Okay, so hello everyone. Welcome to the Bangalore Theory Seminar Series. Today we have as our speaker Arnab Maiti. So Arnab is a second year PhD student at the University of Washington. He is being advised by Kevin Jamieson and Lillian Ratliff. So before joining University of Washington, he was a BTech student at IIT Kharagpur, where he was advised by Palash De. He also did internships from IISc Bangalore, where he was advised by Siddharth Burman and Arindam Khan. So his research interests mainly lie in the field of game theory and learning theory. And today he will be talking about query complexity of finding Nash equilibria in zero-sum games. Yeah. Uh, Without further ado, I'll hand it over to Arnab.
Yeah, thanks, Kevin. So I'll begin the talk. So yeah, this is a joint work with my collaborators at Washington University. So this is on query complexity of finding Nash equilibrium in zero-sum games. So first, I'll briefly introduce what is a two-player zero-sum game. So our main focus will be two-player zero-sum game. So typically in a two-player zero-sum game, you have like two players, some X and Y, and they have like some number of strategies. Okay, so the X player has some n different strategies, and the Y player has some n different strategies. And X typically what happens? X player chooses a strategy I, and the Y player chooses some strategy J, and the X player receives a reward of Aij, and the Y player receives a reward of minus Aij. So for example, the X player can receive a reward of +1 and the Y player can receive a reward of -1. This is a zero-sum game because the sum of rewards is always going to be 0. So such zero-sum games can be properly represented using one single matrix. So we'll be focusing on n cross n matrices, which belong. Yeah, and although I'm talking about n cross n matrices, all the results can be extended to n cross m, where n is not equal to m. So for the simplicity of the talk, I'm just focusing on n cross n. So I'll take you through some notations and some definition. So first, like delta m is going to be an m-dimensional probability simplex. So it's nothing but like a set of all vectors such that each of them, each coordinate represents the probability of choosing that particular coordinate. Yeah. So typically in zero-sum games, there's a concept of Nash equilibrium. So first, I'll give a very intuitive definition of Nash equilibrium. So a pair x star y star from delta n cross delta n. So basically, both are like pair of some probability distributions. So a pair x star y star is a Nash equilibrium if, in some sense, the players cannot deviate from this probability distribution and get a better reward. So during this talk, I'll not use like probability distribution. Instead, I'll use the term strategy. So that's a standard notion in game theory. So this is a strategy x star of the x player, and this is a strategy y star of the y player. So x and y row versus column, I'll just use it interchangeably. So in some sense, when two players play strategy X star and Y star, each of them gets some reward. In this case, the reward will be like same magnitude but opposite sign. And the thing is, like from that reward, they cannot like change their strategy and get a better reward. So if such a pair of strategies will be called Nash equilibrium. So mathematically, what is happening is the value, say, which the X player is getting is X star A Y star. And if it changes from X star to some other X, then its reward is only going to decrease. It cannot increase. Similarly, for the Y player, this is like a loss essentially. So this value will be the loss that it is incurring. So if it changes from Y star to some other Y, so its loss can only increase, it cannot decrease. So loss is like minus of reward. So if such a inequality holds for any deviation, then that pair is called a Nash equilibrium. So before I proceed to the next slide, is the Nash equilibrium definition clear? Or if you have any query, you can ask. Okay, then if there is no query, I'll just explain again with an help of a very small example. Say you have a matrix 3, 1, 2, 4, and the row player is essentially the X player and the column player is essentially the Y player. So when we say the row player chooses a strategy X star, it means that it assigns a probability of choosing the row indices. Okay. And similarly, for column player, when it chooses a strategy Y star, it means that it chooses a probability of like choosing these column indices. So so one can do some calculations and show that this pair X star Y star is going to be the Nash equilibrium of this game on A. So instead of showing you the calculations, we can verify whether this is indeed the case or not. So for that, we have to just verify whether any deviations can lead to better reward or not. So if you take this X star and like do a dot product with columns, then what you'll get is like 0.7 times 3 plus 0.25 times 1, that is 2.5. And same like 0.75 times 2 plus 0.25 times 4 is again 2.5. So this is nothing but this, like A transpose X star. So what it's doing is like if you take this X star and do this, so it's kind of equalizing both the columns. So in that case, what will happen is like if you do compute this product X star A Y star, which is 2.5. This is the 2.5 is the loss which the column player is seeing, but whatever strategy the column player chooses, it will always get 2.5. Okay, in this example. So from the perspective of column player, if it changes from Y star to Y, it will be like this inequality will always hold true. Similarly, from the perspective of Y star, it's like half and half. So just take an average of these two. So you'll get like 2.5 and 2.5. So if the column player is playing this particular strategy, then the reward of each row is same. So whatever strategy the row player chooses, under the assumption that the column player is going to play Y star, the row player cannot do anything better than 2.5. It will always get 2.5. So in this case, like if it changes from X star to X, it's not going to increase its reward. So this example shows that if you choose this X star and this Y star, then that pair is a Nash equilibrium. So it's not always necessary that if you compute this dot product, these products and all, every value will be same. So it's not always the case, but in some good structural matrices, this can be the case that all these values are same. So in some matrices, this can be equality, but in some matrices, this can be strict inequality. And we'll be looking into some of those matrices where the inequality is strict. So before I head to the next slide, I hope everything is fine. Feel free to interrupt me if you don't understand any part. Or drop a question in the chat. Kevin will take care of the questions. Okay. So we have been focusing on this value, which is X star A Y star, which is the reward that the row player gets or the X player gets. So this value is generally known as the value of the game. So typically, when we are studying zero-sum games, it's typically the notion that the row player is trying to maximize its reward and the column player is trying to minimize its loss. So both are in kind of contradiction with each other, or like they're like kind of opposing, they have opposing aims. And there is a very famous minimax theorem by von Neumann, which says that if you take max over X and min over Y and compute this inner product XAY, and then you swap this min and max, then this both they will be equal, and they will be equal to the value of the game. So this minimax theorem in some sense shows that there will exist a pair x star y star which is an Nash equilibrium, and the equilibrium value of the game would be this VA star, which will be the like value that you get for after you solve this optimization problem. So one can easily observe that you can take any zero sum game, and using this minimax theorem, you can formulate it as a linear program and compute the Nash equilibrium. So this is like very well studied and all. The thing which we'll be focusing on this talk is typically in like the optimization side of the literature, they assume that they're given the matrix A, and now they have to come up with algorithms to find a Nash equilibrium. And that's also a very hot area of research. Like, how do you like do things very fast and all? But we'll be having a slightly different focus here. We are looking into mainly a query setting where like the matrix A is not given to us directly at the start. Okay. Instead, what we can do is we can in each say time step, we can query an element ij of the input matrix A and see the value aij. Okay. So so in this case, we are controlling both the players. So so in some sense, this is just an exploration problem. You are given a matrix A, now like choose an entry ij and see the value of the entry. And now the aim is to compute the exact Nash equilibrium of A by seeing as few entries as possible. So typically, like one can just query each and every entry of the matrix and then compute the Nash equilibrium. The question we are asking is, do you really need to see each and every entry of the matrix to compute the Nash equilibrium? Exactly. So that's the main focus of this talk. So the answer is yes and no. Like for some matrices, yes, you have to see every entry. For some matrices, you need not. So we are trying to characterize that here. So the main focus of our talk will be on games with unique Nash equilibrium. We do have some results for the case when the matrix doesn't have a unique Nash equilibrium, but that is not like completely resolved yet. So my main focus of the talk is on matrices with unique Nash equilibrium. One interesting fact about matrices with unique Nash equilibrium is that like if you consider the Lebesgue measure of matrices and all, then the Lebesgue measure of matrices with non-unique Nash equilibrium is 0. So generally speaking, almost all matrices are having unique Nash equilibrium. So we'll be first trying to characterize this particular problem, or we'll try to solve this particular problem for this important case of unique Nash equilibrium. So so since the matrix A has a unique Nash equilibrium, then there are some important properties that are available to us now in this case. So for example, like I don't know if the definition of support is known or not, but it's a very standard definition. So support is so this x star and all are like essentially vectors. So there are like n coordinates. So support is like how many coordinates are non-zero. Okay. So if a matrix has a unique Nash equilibrium, then the support of x star and the support of y star, their size is same. So that is like one important point, which will be very crucial for our talk later on. Now, essentially, the support is where the game is essentially taking place. So if your row is not part of your support, the row is like essentially in some sense suboptimal for the row player. And similarly, if the column index is not part of the support of y star, then the column is suboptimal for the column player. So formally, these are the equations that hold true. So if your row index is part of the support of x star, then this EIA y star, this is essentially the reward you get by playing row I when the column player is playing the strategy Y star, that reward will be equal to the value of the game. But if you like choose a row index I, which is not part of the support, then the reward that you get by playing row I, under the assumption that the opposite player is playing Y star, that will be strictly less than VA star. So clearly, like this row is going to be suboptimal for the row player, so it's better to avoid playing that row. Similarly, for column player, so if it chooses an index J from support of Y star, then the loss that the column player incurs by playing the column J is going to be VA star. And if J is not part of the support of Y star, then the loss that it is going to incur is way more than VA star. So from the perspective of both the players, it's better if they quickly determine the supports and play within that support. So that's the general goal that the players have.
Arnab, one
Yeah.
question from Arindam
Yeah.
sir. So
Yeah.
he asked if there is any intuition why the supports have the same size, like some connections with low column rank, low row rank, like
Oh, yeah.
any.
There are those connections actually. The proof has at the end uses these kind of facts actually.
Okay. So one question from my side. So you're
Yeah.
saying the first line says that for all I,
Yeah.
the Nash equilibrium value is equal
Yeah.
to dot product of EI and AI AY star.
Yeah.
So doesn't that already mean that there are like multiple Nash equilibrium here? Because like all Y which are in this support, they satisfy that
Yeah.
each of
But
them can be a candidate for X star, right?
but suppose you fix some, say you choose only the first row, for example, like say first row is part of the support and you choose
Hmm.
that. So then the column player can deviate then.
Okay, I see.
Yeah, so
Oh,
that
okay.
is a very good example. So for example, this is there, right? So
Hmm.
both the row indices are part of the support of X star. Okay. So now if you just choose this first row, for example,
Hmm.
and this guy was playing half and half. Now it need not play half and half. It can just shift to the second column because 2 is less than 2.5. So it will reduce its loss.
Okay. Okay.
Yeah.
So okay, so Nash equilibrium value may not be the maximum value, but it's the value that they can get without. If
Yeah. So
deviated,
the
then
thing,
they will
okay. So
suffer some loss.
the thing is, there can be multiple pairs XY such that this inner product XAY that can be equal to VA star. Okay.
Ah,
But this doesn't mean that X comma Y is an Nash equilibrium.
right. Understood. Yes.
Yeah. So the opposite is true. Like if X comma Y is an Nash equilibrium, then X AY is equal to VA star, the value of the game.
Sure. Understood. Yeah. Thanks.
Yeah. So that is a fine distinction between both of them. Okay. So I hope there are no more questions. Okay. Yeah. So there might be a question of, okay, so why do we hope that we can find the Nash equilibrium without querying all the entries of the matrix? So this can be a good motivation to begin with. So say the support size of X star, which is also equal to Y star, is equal to K. Okay. So we'll be parameterizing in terms of K in this talk. So typically a matrix has n square entries, but our goal will be something like n times polynomial of K. So if K is small, then this is like way less than n square. So now like you might wonder, okay, why is it the case? Like why do we even think about solving this particular problem? So if you recall the definition of X star Y star being a Nash equilibrium, this particular inequality should hold. Okay. Which is like X star A Y star should be less than X star A Y and this should be greater than x a y star. Okay. Now, if you observe this inequality, the elements which affect this inequality are the ones which are in this shaded region. So these are the row indices corresponding to x star, and these are the column indices corresponding to y star. Okay. So if you look at this part of the inequality, so y star is fixed. Okay. So you're taking y star and doing a dot product with every row in some sense. So this part of the y star is 0 essentially. So these all will get multiplied by 0. So whatever changes you make here, it will not affect this part of the inequality. Similarly, if you go towards this side, x star is fixed and only y is changing. So essentially this is fixed here and only y can change. So this part of x star is 0 essentially. So again, this won't affect this side of the inequality. Only if you make changes here, it will affect this. So in that case, you can see, like if you take a union, like this portion, this white huge portion is irrelevant to the inequality. Whatever changes you make here, it won't affect this inequality. So it kind of says that there are a lot of matrices which are sharing the same Nash equilibrium and even the same supports. Okay, essentially. So, and the relevant elements are roughly of the order n times k. Okay. So it says that, okay, if only n times k elements are affecting the Nash equilibrium, then it might be the case that, yeah, like you need some n times, say, polynomial of k to find that Nash equilibrium. So this is indeed going to be the case in our talk. So before we proceed there,
Question in the previous slide. So like in the gray region also is the like top left square, right? Like which is relevant. The others don't. The other gray regions, like how do they matter?
How do they matter is like say okay, say like you're by playing this strategy, you're getting something like 0.5, for example. Okay. And say initially the elements here are like 0, 0, 0. I can change this and make it like 1, 1, 1, 1, 1, right? Every element in this region.
Yeah,
so,
but
so whatever
like,
strategy is being played here, the dot product with this is like going to be 1, and that's more than the value of the game. So this has to change and deviate to this row here.
Oh, okay. So again, deviation. This thing. Okay, fine.
Yeah.
Sure.
Yeah. So this part of the matrix is very important, but this part is not.
Sure.
Yeah. So whatever I told now, this can be properly formalized, and we can show that any algorithm will require n times k entries in expectation in order to find a unique Nash equilibrium. I should have told at the start that the algorithms that we'll be designing is mainly will be randomized algorithms. So with high probability they are going to find. I'll talk about deterministic towards the end. Like that part is still kind of open, but I'll talk about it towards the end. But right now, our main focus is going to be on randomized algorithm. So even in randomized, it's not clear like how do we do in sublinear. And a first step is like, okay, at least you start with a lower bound. So any randomized algorithm will take at least n times k entries to find the unique Nash equilibrium. So the next immediate question is, can you design an algorithm which with high probability queries some n times polynomial k entries of the input matrix and finds the Nash equilibrium? So so that's going to be the main focus of our talk. So a good place to start is with a very special case, which is k is equal to 1. Just a second. Yeah. So this k is equal to 1 is a special case because when the support size is 1, it is essentially called pure strategy Nash equilibrium in game theory. And in terms of matrix also, it's pretty interesting. So essentially what this case boils down to is you have to find an entry in the matrix, okay, some entry I star j star, such that the entry is the highest in its column and the lowest in its row, and it has to be the unique highest in the column and unique lowest in its row. So essentially, like, this entry has to be the highest in its column. So for all I not equal to I star, I star I j star is less than I star j star, and similarly for all j not equal to j star, I star j is greater than I star j star. So this element I star j star is the highest in its column and the lowest in its row simultaneously. So such an entry is called pure strategy Nash equilibrium. So you have n square matrices. The question is, can you find this entry, say, in nlog n query? So without looking at the entire matrix, which has n square elements, can you find this special entry if it exists? So you can see verification is quite easy. Like, if I give you a entry I star j star, then you can just like check the element in its row and elements in its column and just verify very quickly whether you can find it, whether that is a Nash equilibrium or not, like pure strategy Nash equilibrium or not, PSNE in short. But to find it in such similar time step, for that we need some like clever algorithm, and that's what we are going to design. So the rough idea of the algorithm is like, so there will be some logarithmic number of stages, and in each stage we'll be trying to like remove half of the columns and half of the rows. Like, we want to remove half of the rows and half of the columns, which will not contain that special entry which we are focusing on, which is the PSNE. So we'll be removing the bad columns. So all those columns which are not equal to I star. So we'll be removing them in logarithmic number of stages. So in the first stage, we'll remove half of the rows and half of the columns. So we show the procedure for rows, like how do we remove half of the rows? A similar procedure will exist for the column. So that's like, that will be clearly evident once I show you the algorithm. So yeah, so yeah, so we have to find, we have to ensure whatever we are doing, we don't kick out I star j star. Okay. So the first thing which we do is we choose some logarithmic number of row indices. Okay. So we choose some log n, like delta is just the confidence parameter, like with how much probability error are you willing to accept. So ignore the delta for now, assume it's constant and something, but main focus is like log n. So choose some log n number of row indices. Now query each and every entry in this row, in these rows. Okay, so the gray cells represent queried entries. Now, next thing that you do is, if you observe column wise, there have been some elements that
These
have
entries
been
are chosen randomly.
Oh yeah, they're chosen randomly, like uniformly at random.
Okay.
Yeah, yeah. Choose the row indices uniformly at random. And then once you choose them, then query all the elements in those rows. Then if you look at some particular column, so there are some elements that have been queried in that column. So in this case, there are like 4 elements that have been queried. So for each column, keep track of the highest element that you're seeing in each column. Okay, highest. Okay, so in this column, among the among the entries that have been queried, this is the highest entry. Same is the case. This is the highest entry, highest entry, highest entry, and so on. So in a column J, if this is the highest entry that has been queried, so I'll just denote it by Vj, a value Vj. Okay. So the next step that I do is I find that column J hat, which minimizes this value Vj. So I'll find that column which is like argmin j vj, and then I'll query all the entries in this column. Okay. So I'll query all these entries in this column. And once you query, you can, just for the sake of simplicity, like you can like swap the rows and columns that won't like affect the Nash equilibrium, in the sense that only the indices names are changing, but you can find the entry at the end. So just for the sake of simplicity, assume that the entries that you queried, they are in a decreasing order. Okay. If that's not the case, you can just swap the rows. That won't be an issue. So we are finding this j hat, which is like minimum over all vj's, where vj's were the highest queried entry in each column, and say we have sorted them in a decreasing fashion. Okay. And the only thing we do is we just return the top half. So this is from A1, A2 up to AN. So this is the inequality. And we discard all those rows which are there in the bottom half. And you can do a similar procedure for the columns. Remove half of the columns. Just you have to go in opposite signs, like instead of maximum C minimum, instead of minimum C maximum. And these inequalities gets reversed. But just the idea is same. And you can even reduce the number of columns by half. So this is the algorithm. So now I'll like give you the reason why we'll not throw out I star J star. I think the algorithm is pretty simple to understand, so it shouldn't be an issue. But feel free to interrupt anytime. It's also easy to see that the number of queries we take will be nlog n, because in each stage we are taking like if there are like n rows and n columns, we are taking essentially order n queries. And if you do the math, you can show that the number of queries taken is n log n, because in each row, in each stage, the number of rows and columns are just decreasing by half. So that's an easy calculation. So the main question is the correctness of our algorithm. Like, why is our algorithm correct? Okay, with high probability, especially. So let's start with the totally n stage. Okay. So if you recall, we were keeping track of highest element in each column, and then we looked at that particular column j hat, which took the least value among those highest values. Now, if you look at the value vj hat, okay, so some entry of that column j hat corresponds to that value vj hat, because those are the values of some entry. So with very high probability, this vj hat will belong to the top half. Okay. You can just do the math. Like if you're sampling for log and logarithmic number of times, then so with probability half, it can be in the top half or it can be in the bottom half. Probability that each time it is in bottom half, it's like half to the power log n, which is very small. So with high probability, the entry which corresponds to the value vj hat will be in the top half here. Okay. So vj hat was the just to recall. So vj's was these value, like so initial queries that you did and the highest among them. So that is like the vj hat that you'll see. So that particular thing will be in this top half, which means that the bottom half of this particular column j hat, their values will be at most vj hat. Okay, because this is in a decreasing order, so their values will be in the bottom half. Now let's focus on the row, our for column of focus, which is j star. If j hat is equal to j star, it's very trivial because I star would be the highest element in its in this column. So if we discard half, the bottom half, it's fine. We are not going to throw out I star. So the interesting case is when J star is different from J hat. So as I told, like this I star J star element will be the highest in this column anyway. So this Vj star will be less than equal to A I star J star anyways. Now by definition, this J hat was argmin of those Vj's. So Vj hat would be less than equal to Vj star. Okay. So these this bottom half entries are at most Vj hat. So Vj hat is essentially less than A I star J star. So these bottom half entries are at most A I star J star. Now let's focus on the column I star. Now by definition, this I star is the unique least element in this row. Okay, which means that any other column, this A I star J star will be strictly less than A I star J hat. Okay. So which means that if you focus on this value here, it should lie in the top half because the bottom half elements have a value which is at most A I star J star. So I star cannot lie in this bottom half. So we can like safely remove half of the rows and retain I star. And we can then proceed to the next round. Like in similar fashion, you can remove like half of the columns. And in the stage by stage process, you can at the end you will end up with just one single element, which is I star J star, and that will be your Nash equilibrium or the unique pure strategy Nash equilibrium. Yeah. So before I proceed to the arbitrary k size case, so is there any query regarding this algorithm or its analysis?
So this so now n cross n is becoming n cross n by 2. So does that
No,
result about?
the thing is like you can do the same thing parallelly from the column side. So both are operating on n cross n matrices. From one side we are working on like from the perspective of removing half of the rows, and on the same n cross n matrix we are operating from the column side. So at the same time we are removing half of the rows and half of the columns, and so the matrix will shrink from both dimensions.
Okay. No. So my question was we use this fact that like support of x star is equal to support of y star crucially, right? That I think you mentioned it only in the case of like n cross n matrices. Does it hold for n cross n also?
No. That's a general statement, like not just for n cross n.
Okay, fine.
Yeah.
That was my question. Okay.
Yeah. So the thought of, okay, whatever I am saying that can be easily extended to n cross m games also, especially that those properties that I told. So it has nothing to do with the shape of the matrix, initial matrix. Yeah.
Fine. Thanks.
Yeah. And also there is this property which I did not say, but if you take a larger matrix and somewhere the support is lying, and then you reduce the size of the matrix, and the entire support is still in that matrix, then that smaller matrix also has a unique Nash equilibrium with that same support. So in this case, like even if you take like if you reduce from n cross n to n cross n by 2, which we are not doing, we are like reducing both dimensions, we are reducing by half. But in case if you assume that you only reduce the row dimension, still this I star J star will be the only Nash equilibrium of this entire game. So as long as the complete support is there in this submatrix, the Nash is not going to change. That is not a easy proof. Like it's not so easy to see. You have to do some manipulations, like proper calculations and all, to show that that is the case. But as long as your supports are there in your submatrix, nothing is going to be changed in the matrix. Yeah. And in this case, it's very easy to see, like if this I star was the lowest element in the original matrix, it's going to be the lowest element in the smaller matrix as well. And same goes for the J star. Like if that was the highest element in the original matrix, it is going to be the highest element in the smaller matrix as well, because we are not adding any new elements, we are just removing them. Yeah. Okay, so if that's clear, then I'll now go to the case of arbitrary k. So some people might assume, okay, what was the need for k is equal to 1? Like we could have directly dealt with k. Surprisingly, we show that you can take this arbitrary k case and reduce it to the case where k is equal to 1. So what we'll do is, like, we'll consider matrix x star y star, sorry, we'll consider matrix A with Nash equilibrium x star y star such that the size of the support is k. Now what we'll do is, using this matrix A, we'll create a higher dimensional matrix, some AK. That's just a notation. And we'll show that this matrix has a Nash equilibrium, and that Nash equilibrium, this matrix has a pure strategy Nash equilibrium. And that will in some sense correspond to the support here of this original matrix. So let me present the way to construct this higher dimensional matrix. So this matrix is like high dimensional. So it will have like n choose k number of rows and n choose k number of columns. So let's label them as 1 to up to n choose k. Same goes for here. And say this is the original matrix A that we are concerned with. Now, each row index here in this higher dimensional matrix A is mapped to a unique set of row indices of size k. Okay, so there's some bijection mapping between the row index here and set of all indices of size k. So there's some bijection here. So any row I here is mapped to a subset of indices I1, I2 up to Ik. Okay. Similarly, each column index here, J, is mapped to a unique set of K column indices, J1, J2 up to Jk. Okay, so there's some bijection mapping between the row index and the set of row indices and column index and the set of column indices. Now we have to fill these matrix entries. Okay, so how do we fill? So choose, say we look at an arbitrary entry ij. Okay. So the ith row corresponds to the set of indices I1, I2 up to Ik, and the jth column corresponds to a set of indices J1, J2 up to Jk. So you can consider the submatrix B in the original matrix A such that the row indices are this and the column indices are this. So this will form a K cross K submatrix in the original matrix A. And you can consider this matrix and compute its Nash equilibrium value. Okay, so you can compute this max over x, min over y, x, by, and that value you can feed it as the value of this entry in the higher dimensional matrix. So this is the way the higher dimensional matrix is being created. So I hope this is clear. So this is just like bijection mapping and then taking the Nash equilibrium value and then fitting it here.
So like we don't know k, right? Is there a way to know k?
I mean, assume you know the k for now, and later on what you can do is like you can start with k is equal to 1. Then you'll get some garbage value, garbage basically, like some garbage x comma y. You can easily check whether that is a Nash equilibrium or not, and then you can keep on increasing k until you hit the actual k, and then you'll find the value correctly. Okay. So this will just like make you incur an additional factor of k.
Okay.
So now if you whether you can improve upon this and all, that's an open question, but it's still going to be n times polynomial of k. So knowing the value of k is not that crucial.
Okay.
But for now,
And,
like I should have told properly, but for now, assume you know the k.
Okay. And like when k is equal to n by 2, so the size of the matrix, this high dimensional matrix will be like exponential. Or like
It's
something.
exponential. Yeah. So this is like,
Okay, so
so this is not a exponent. It is not a polynomial time algorithm, as you can see, because if the matrix sizes are huge, then I mean, if k is huge, then the size will blow up. So that issue is also there, whether this you can do it in polynomial time or not. But our main focus was to just establish the query complexity. Like what is the number of queries? I'll explain how why the queries will be m times polynomial of k still.
okay.
Yeah. Why the queries won't blow up? Time complexity will obviously blow up. So I can't do anything about that for now. Yeah.
Sure.
Yeah.
Okay.
So one small example is this. So for example, if this is the original matrix, so you can construct a larger high dimensional matrix. So each index is mapped to some set of two indices, which is a bijection. And if you look at this orange, okay, if you look at this entry here, orange entry, this corresponds to row indices 3, 4 and column indices 1, 2. So this thing will correspond to this here, this submatrix. And the value of this game is half, like it's a very symmetric game. So the half and half, half and half. So it's 0.5. So you have to feed 0.5. And in similar way, you can fill the rest of the matrices. Yeah. So now what I claim is that this higher dimensional matrix AK, this should be an exponent, but yeah, this higher dimensional matrix AK has an entry I star J star such that this like the in this column J star, this entry is the highest unique highest element, and in the row I star it is the unique lowest element. Okay, so this I star J star will be the PSNE of this higher dimensional matrix. So it will be a pure strategy Nash equilibrium. So precisely these inequalities will hold. So if you fix a J star and change I, then the value will only decrease, and similarly here the value will only increase if you change J. So it will be the unique highest element in the column and lowest element in its row. And the interesting fact is that the bijection mapping which we do, so in that bijection mapping, I star will map to the support of X star, and J star will map to the support of Y star. Okay. So essentially, we can take our algorithm for k is equal to 1 and run it on this huge matrix. And once we find I star J star with high probability, we just need to look at the mapping. Okay, what did this guy map to? Support of X star. What did this guy map to? Support of Y star. So that submatrix will end up getting a k cross k submatrix. So once we have that k cross k submatrix, we can directly compute the Nash equilibrium. It is just a matrix inversion, and also that's very easy, and you just need to see those k square entries. So the key part is, how do you find this I star J star? I mean, we can find, our algorithm does it for k is equal to 1. So that's why I presented k is equal to 1 at the start, and then I shifted to this particular case. But now the question is, as Kevin was asking, like if k is large, then this matrix blows up, right? It's a huge exponential size matrix. But how can we ensure that the number of queries is still small? Before I go to that explanation, just like again the same example, but here you can see. So you can show that the support of the Nash equilibrium here would be like 3, 4 for the row and 1, 2 for the column, and you can see the 0.5 entry is the lowest in its row and the highest in its column. So so this thing is there. So now let me kind of explain why there won't be an exponential blow up or any, like, first of all, there's no chance of exponential blow up because the number of entries in A, in the original matrix A, is just n square. So we have to show why it's like n times poly k. Yeah. So the main thing is I want to show why is the query complexity n times poly k. So just for sake of completion, like we take our algorithm for k is equal to 1 and run it on this higher dimensional matrix to find this entry I star j star. So okay, so if you recall, in our k is equal to 1 algorithm, we focused on we chose some logarithmic number of indices uniformly at random. So in this case, it is like n to the power k, like n choose k is upper bounded by n to the power k. So this is roughly like k log n. Okay. So you're choosing some k log n column indices, row indices of this higher dimensional matrix. Now, a key thing to observe is, say you want to query all the elements in this row I of this higher dimensional matrix. Okay. Now, at first it appears that, okay, there are like n choose k row indices. There are n choose k elements here. So there might be some blow up, right? But if you observe more carefully, this column this row I was mapped to some k row indices in the original matrix. Okay. And the values here are kind of uniquely determined by these values here only. So for example, if you consider any entry here, so since it's part of row I, it will the row part will map to this I1, I2 up to Ik, and the column part will be some subset of 1 to n. Okay. So this subset would be of size k, but the thing that I wanted to focus on was, if you want to compute every entry of this row I, all you need to do is query all the entries in these k rows. Okay. And once you do that, so essentially you'll be querying like n times k entries. So so there are like k rows and n columns. So if you compute all these n times k entries, then you can look at any entry here. So it will correspond to a k cross k submatrix here, and you can compute the entry. So actually there is not an exponential blow up. We are still within our desired regime. So we are within n times poly k only. So here to measure this entire row I, we require like n times k. So similarly, like in our entire algorithm that we did, we were only like measuring continuous elements in a row and continuous elements in a column. That's the only operations that we did. And number of times we did this operation was some logarithmic number of stages. So here like it's log n to the power k, which is like k log n. So at the end, when you do all the calculations, it will just turn out to be n times poly k. So there won't be any like very hi-fi blow-ups that's happening. So let me know, like this part can be slightly confusing. So if you have any queries, let me know why there is not a blow-up and why we are within n times poly k. Kevin, is this part clear? Like why it is?
Yeah, it's clear. Yes.
Yeah, because we can essentially reuse the elements that we query. So the main concern is A, not A to the power k thing. Yeah. And as you were asking, what if we don't know k? We start an algorithm with k is equal to 1, 2, 3, and so on until you find the Nash equilibrium. And the verifying is very easy. So you just need n times k entries to verify whether some given xy of size k is a Nash equilibrium or not. If you go back to the very first initial slide that I showed, which entries are important, that's also helpful here. And then because of this, we'll incur an additional factor of k, but it's still like like n times poly k. The exact expression is n times k to the power 5. Like after doing all this, so it's that if you can close down the gap between lower bound and upper bound is also a very good question. Yeah, so this was the deterministic side of the thing. So I'll not explain. Sorry, this was the randomized side of the things. In general, deterministic is open. Like if you consider k is equal to 2 and on, currently we don't have any algorithm which can do it better than n square. So that's an open question for now. But for k is equal to 1, what we showed, I'm not going to explain the algorithm here, but what we showed is like you can identify that pure strategy Nash equilibrium using just like 3n minus 2 queries. Okay. So these are very, this was kind of like a puzzle question. So like to verify whether an entry is a Nash equilibrium, like pure strategy Nash equilibrium, which is essentially whether an entry is the unique least in its row and unique highest in its column. In order to verify, you need 2n minus 1 queries because you need to query the row and the column. But here we are saying that within 3n minus 2 queries, you can actually find this PSNE. Okay. This algorithm is totally different in style than our randomized algorithm. That's why we cannot apply it for higher dimensional matrices. But I'm not going to explain the algorithm, but the key part of the algorithm is this, essentially, this particular property. Let's say if you query, so here the queries essentially take place diagonally. So if you query diagonally, say 1, 2, 3, 4, like if these are the values that you saw, then you can immediately rule out a lot of elements which cannot be the PSNE. So you can rule out all these cross-marked elements and they will never be PSNEs actually. The reason being that for PSNE, say this element has to be the least in its row and highest in its column. But how can an element be more than 2 and less than 1? That's not possible, right? So this is the entire like kind of the logic behind the algorithm. So if you cleverly sample diagonally and cleverly eliminate rows and try to retain some elements as candidates for PSNE, and then you can end up finding the PSNE in just 3n minus 2 queries. Like you have n square entries in a matrix, and you can find it deterministically using just 3n minus 2 queries. Yeah.
So in the randomized setting, you were using like some n log n number of
Yeah,
queries.
yeah. So it also improves that as well. But the thing is, like that algorithm is also required because we want to solve the higher dimensional case here.
Right. Okay.
Yeah. The thing is that since we are querying diagonally, so if you try to query diagonally in the higher dimensional matrix, immediately it will lead to n square queries. Okay. So
Okay.
so that's why we cannot apply this algorithm to the higher dimensional matrix. So that's why you need some, I don't know, like whether it's possible or not, that's also an open question. So is there any like dichotomy, like, okay, randomized possible, deterministic not possible? So it's a very interesting open question.
Okay.
Yeah.
Fine.
So so this leads to the open question. So the first open question is like, as you saw, like the bounds, although like it's n times poly k, it's not optimal yet. So the first question is what can you obtain, like what can you improve the algorithm and find optimal bounds for randomized algorithms up to logarithmic factors, say. Then as I was saying, does there exist deterministic algorithms for k greater than 1 case? And the last case, which is what can you say about non-unique Nash equilibrium? Here I'm not here, like the most important thing is like how do you even characterize, because there's no concept of support size anymore because there are like multiple Nash equilibrium with multiple support sizes and all. So what is a proper thing and all? So we do have one small result which kind of extends the our old results, is like if your Nash equilibrium is if it is a convex combination of multiple pure strategy Nash equilibrium. So if you choose any Nash equilibrium, if it is a convex combination of multiple Nash pure strategy Nash equilibrium, then we can find some sublinear algorithm, and there we can define a appropriate k and do it. But for the general case, one first needs to identify, okay, what's like a proper parameter to characterize and then build an algorithm upon it. Yeah. Yeah. So thank you, and let me know if you have any further questions regarding this.
Thanks, Arnab, for this nice talk.
Yeah.
Any questions from the audience? So another question from my side. So,
Yeah.
so what's like the number of queries taken is like n times poly k. I believe
Yeah.
the poly factor is like around n is something like n times k cube, right?
Sorry. Yeah. Sorry. The k to the power 5 was for a different algorithm. So it's n times k cube and since if we don't know k, then the another additional factor of k will pop up. So it will become n times k to the power 4, not 5. 4.
Right. Okay.
Yeah. You're right.
N times k to the power 4. Okay.
Yeah.
So if k is like very sparse, it's like less than n to the power 1 by 4, then
Yeah.
we'll need like less than the trivial number of queries.
Yeah.
Yeah. Otherwise, it should be seen.
Yeah. So now the
Okay.
important question is like, what is the optimal k to the power thing? Like,
right.
yeah, like n times k would be too optimistic, but I don't know. Like the current lower bound is just n times k. So
Okay.
yeah, so the current
Okay.
lower bound essentially says that if k is small o of n, then it is like small o of n square. But does that translate to an upper bound? Like if you are like small o of n, then does it mean small o of n square? So I don't have an answer for that right now.
Okay.
Yeah, like to even get to this n times poly, k was like a first step towards addressing this problem, because in general, like the thing that people do is like, okay, they run some kind of learners like exp3 or something like that on both sides, and they converge in an approximate sense, and they take n log n by epsilon square steps to converge to some epsilon Nash equilibrium, but nobody talked about exact Nash equilibrium.
Okay.
So this was kind of a first step towards the exact computation.
Okay. Yeah. So Arindam sir is like asking a question like along those lines. So what is known in the approximate setting, like approximate Nash equilibria?
So for approximate, there are two key things. First thing is they assume that entries are bounded between 0 and 1. This is a very critical assumption. And then
Okay.
it is known that if you take n log n by epsilon square steps queries, you can find an epsilon approximate Nash equilibrium. The matrix can have multiple Nash equilibrium, unique Nash equilibrium. That's not an issue. But within n log n by epsilon square time steps, you can find an epsilon approximate Nash equilibrium. But
Okay.
for that, the crucial thing is the entries of the matrix have to be bounded between 0 and 1. Because if the matrix are bounded between, say, 0 comma b or something, that b also comes into the query complexity thing. Because these learners are very much dependent on the value, whereas our thing is just comparison based. So yeah, so our results hold for any arbitrary matrix in real number space. Yeah.
Okay. Okay. Yeah. Cool. Yeah. Thanks for this nice talk.
Yeah.
Yeah. Let's thank the speaker again.
Yeah.
I'll stop recording.
Yeah.